or two.
Right.
Okay, sir.
Right, Javad.
I'll just run coffee.
Let's we'll continue. If you remember, ladies and gentlemen, we talked about the production of uranium hexafluoride, which for our purposes, we're going to talk about being a gas, but bear in mind at its triple point, round about 70 degrees centigrade, it can exist both as a gas, as a liquid, and as a solid. Why have we produced uranium hexafluoride? And we produce uranium hexafluoride in thousands of tonnes per year, and this is to make enriched nuclear fuel. Why do we excuse me, why do we use fluorine in addition to the fact that it produces uranium hexafluoride, a very interesting chemical reagent? Fluorine does not have any isotopes. If it did, it could complicate the process, but fluorine is monoisotopic and therefore is very helpful for the enrichment process that we will discuss next. Okay, the UF6, as I mentioned, we produced at Springfields. We actually transported it from Springfields to Capenhurst on the outskirts of Chester, and its transportation was carried out in 48-inch cylinders. Please remember at this stage that the uranium is still in its natural isotopic composition. So we're talking about 99.3% or thereabouts as U238 and 0.71% as uranium-235. And this is why we can use 48-inch cylinders. You will see later, after the enrichment process, we use much small diameter cylinders. Okay, right, so we're talking about enrichment. And let's just move it along a little. Right. And excuse me, how can we enrich uranium? There are various schemes for enriching uranium-235. Only 2 of them to date have been used on a commercial scale. The first actual process that was which was developed to a certain extent, but not above the laboratory scale, was this electromagnetic means. And if we'd have got chemists amongst us, then they would have appreciated that the inductive coupled plasma scheme that you use for analytical purposes of elements, ICP-MS, for example. In actual fact, it's that type of process that was first considered for uranium enrichment. It could not at the time be perceived to be scaled up to a size where we could be handling 1,000 tonnes of uranium hexafluoride on an annual basis. What could be scaled up was the second approach that the industry had evaluated, was gaseous diffusion. Gaseous diffusion is still used in many countries. We discarded gaseous diffusion about 20, possibly a few more years than 20 years ago. And one of the reasons for that is gaseous diffusion is a heavily energy consuming business. And how the diffusion process works, as it's showing you here, is you actually squeeze, for want of a better word, the uranium hexafluoride molecules through very small orifices in a membrane. Okay, and obviously this is a physical separation, not a chemical separation. And because the size of UF4 and U235 and 238 isn't significantly different, probably about 0.002% in size. Bear in mind, we're comparing 235 and 238, okay? Then, as with not just the gaseous diffusion process, but also with, which we will talk about next, the gaseous centrifugation process, you have to carry out this separation process a multiple of times. And the gaseous diffusion plant, when it was around at Capenhurst, and you may recall those of you who came on the N04 course to do with decommissioning, when we decommissioned, we being BNFL, we actually produced something like, we cleaned up, but we produced 10,000 tonnes of aluminium, because the gaseous diffusion plant was manufactured of aluminium components. The size of the gaseous diffusion plant, at the time at Capenhurst, was the largest building in footprint in Europe. It was a massive building. It required literally its own nuclear power plant, its own electricity plant, to actually run the actual gaseous diffusion. It was so energy intensive. Effective, yeah, but energy intensive. And people were looking at other ways of how to separate 235 away from 238. And in inverted commas, more recently, it was shown that we could do this simply by spinning the U235 uranium hexafluoride and 238 uranium hexafluoride. And because of the difference, very small difference in weight, for want of a better word, then we could separate them by a centrifugal force, where, which we'll talk in a few minutes, is what happens in a gaseous centrifugation plant. Okay, there are a gaseous centrifugation plant. Yes, beg your pardon. There are still gaseous diffusion plants around. Why? Because, not surprisingly for our industry, the nuclear industry, if it still works, why not keep using it? Because to replace it then costs a small fortune. And if it's working and it still meets with the regulatory authorizations in terms of safety operations and possibly from an environmental impact, but let's forget about the energy for the time being, then why stop using it? Because bear in mind, whether it's gaseous diffusion or gaseous centrifugation, a uranium enrichment plant produces very few wastes. Residues, yes, waste, and we'll come on to residues later. Waste, very few indeed. And because Capenhurst is an inland site, then the discharges to its watercourse are severely controlled, and you're talking about levels probably down at less than a few parts per million being allowed into local watercourses from the centrifuge enrichment plant at Capenhurst. So we've moved on now from gaseous diffusion to gaseous enrichment by centrifugation. And this slide here is indicating to you a representation of what a centrifuge, a single centrifuge, looks like. Bear in mind, centrifugation and gaseous diffusion are no different when it comes to, we are talking about requiring a multiple number of stages, probably a few thousand stages. And that's why gaseous diffusion, or one reason why, it was so expensive. You couldn't just pass it through one membrane and go from 0.71 up to 3-4%. You probably, as we've indicated, had to pass it through a membrane a few thousand times. Just think about it. The difference in atomic size, 238 and 235. That tells you about the numbers or the efficiency of separation. Although may be good, it's still small. Okay, so we're using now gaseous centrifugation. And again, if you remember when we talked about decantation thickening, I suppose this is in some ways a bit similar to decantation thickening. Decantation thickening relied on gravity. And we got a good separation because of the good differences in densities, and therefore, if you like, yes, because of the densities. Here, the difference is very, very small indeed. And therefore, we have to impose on the 235 and 238 a centrifugal pressure. And what happens in that centrifuge is the 238 will collect near the rotor and the 235 to the outer, or I think it's the other way about, to the outer extremities of the centrifuge. You probably, when you were involved in A-level chemistry, you may have used a centrifuge, as we talked earlier about separating solids and liquids. And your centrifuge in the laboratory was probably going spinning around at a maximum speed of a Black & Decker drill, 3,500 revs per minute. These operate at 50,000 revolutions per minute. And once we get these, and these are built of aluminium, lightweight material for obvious reasons, and once we get them up to speed, they will continue spinning without adding a great deal of emotive force. Again, why centrifugation is, let's say, highly more efficient energy ways than the actual gaseous diffusion. And not dissimilar to gaseous diffusion, the more enriched uranium hexafluoride goes, if you like, stage left, and the less enriched uranium hexafluoride goes right, for want of a better description. Because bear in mind, what we're doing is altering the ratio of 238 to 235. We're not producing anything, we're changing the ratios. We don't produce U235, we just separate it away from 238 and produce a slightly more enriched uranium 238 in a different stream. Now, once we've got to the required uranium value, we again, because this is a gas, we then pressurize and put under conditions where we can run off the uranium, enriched now uranium hexafluoride, into a cylinder for transportation back to, for example, Springfields here in Preston. Bear in mind, we're now talking about 235 that could be 3 to 5% enriched in uranium. 235. And what that tells you now is criticality. So we actually now use a much smaller, something like a 24-inch diameter cylinder because of criticality considerations. Okay? What people are looking at even today, even though uranium centrifugation process has gone into something like 6 or 7, it could even be more than 7, further developments, because this is what happens with any production process. You see more and more models come out. If we're talking about motor cars, if you've ever seen a photograph of a Model T, Ford Model T motor car, compare that now with the cars you see on the street, there is no comparison. And this is true of centrifugation. It's undergone iterations and further iterations and even further. And as a result, any potential competitor has been crowded out. I mean, nowadays, gaseous diffusion would not be anywhere near comparable to gaseous centrifugation. But people are looking at laser enrichment, full stop. I think possibly Star Wars was a good starting point to kindle the interest in lasers and laser enrichment. And people believe at the moment this could surpass gaseous centrifugation. We in the United Kingdom, about 30 years ago, excuse me, we did have a look at laser enrichment. We actually built a pilot plant. I don't think we ever switched on the pilot plant or the demonstration plant, excuse me, because again of this iteration from centrifugation. Every time someone came along with an idea, centrifugation had moved to the next stage and become even more attractive. But laser enrichment is becoming excuse me, even more interesting because it offers certain opportunities that centrifugation may not. And these opportunities are being able to select preferentially uranium-235 as opposed to uranium-238. And it's that preferential selection that where you can excite 235 and not excite 238 that people believe is the opportunity that laser enrichment brings to us. Okay, I'm not quite sure what this next, and this is, beg your pardon, I should have put you on to that particular overhead presentation. There's a good deal of description in the notes pages on that laser enrichment, and here we're talking about the actual profile for the enrichment process. This one, yeah, it should be tremendous if I could see these slides, you know.
I'll have to have a look at that. Are you okay there?
Oh, beg your pardon. Yeah, I'm okay. Sorry, ladies and gentlemen. Yeah. This is a process, Chemex. And if you remember, we said that the actual 235, 238 separation is a physical separation. In terms of enrichment, whether it be laser, whether it be centrifugation, whether it be diffusion, that are largely physical, if not exclusively physical processes. But this one here is a chemical process. And when you talk to people about chemical enrichment, they think, hang on a minute, Ali, there's something wrong with this, because 235 and 238 are associated with the nucleus. What the deuce is happening here? And basically what happens here is to do, and this is why we mentioned this, is to do with complexes and kinetics of 235 and 238. Now, the French, they produced a process called Chemex, and the Japanese, and Chemex was based on a liquid-liquid extraction process. Oh, the Japanese process was based on ion exchange. And I'll be honest with you, I forgot what, unless it's on that slide, I forgot what the Japanese call their process. And I can recall being at a meeting, a nuclear meeting in the United States, and the Japanese first announced their ion exchange process for enriching of uranium-235. And the skeptical people thought ridiculous. And they suggested to the Japanese people present at this conference, they would never be able to enrich uranium-235 to around about 2.5%, certainly not up to 5%. It would be near impossible, if not impossible. So the Japanese took this punch on the chin, so to speak, and they went away. And they came back the next year. This was a regular annual nuclear energy, not necessarily just energy, but nuclear processes as well, including reprocessing. And the Japanese came back, and we were able to go to the following year, and the Japanese then told the audience that they had produced enriched uranium-235 to 2.5% enrichment value in under 12 months, to take the audience by complete surprise. However, in fairness, the Americans were right. They were both right, both the Japanese and the Americans. This Japanese ion exchange process is no longer being pursued, and neither is the Chemex process that the French developed. The French process never got beyond 1%, 1.2% U-235 enrichment. Why have they stopped? Very simply because gaseous centrifugation was now, certainly as far as the UK and two other operators, starting to dominate the scene. Laser enrichment, there was that twinkle in the physical chemist's eye that this will ultimately make the day, but not yet. And the Japanese thought, and the French, their two processors had probably missed an opportunity. And when you're developing technology, ladies and gentlemen, that's something that you need to bear in mind. When you started with the idea, and it's probably taken you 10 years to get the idea ready to commercialize, is that opportunity still there? It's important. And you need to keep your research development under continuous scrutiny to make sure that there is no one suddenly got something better than you're thinking you're going to produce, but haven't quite got it to that scale. This slide, ladies and gentlemen, tells you how to calculate how much natural uranium you would need to enrich to get a particular quantity of enriched uranium at a certain enrichment point or value, beg your pardon. I'll not go through it. It's a typical, and I don't think, Jabbar, I'm giving away too many hints, It's a typical small question that would be used for an examination. For example, how much depleted uranium would be produced from enriching natural uranium, starting with 1 tonne, and you're enriching it to 5%, 235. And that equation will tell you how to calculate how much residual or depleted uranium you would finish up with.
What do the PW subscripts mean? What do the PW and F subscripts mean?
Okay, and it's that enrichment or depleted uranium, ladies and gentlemen, that, if you like, is the Achilles heel of enrichment. What do you do with something that has 0.2, 0.3% 235? And we've got in the United Kingdom something like either depleted or low enriched or natural uranium. We've got something like 100,000 tonnes. And what will we do with it? That's the challenge in terms of sustainability. Right, we've now got enriched uranium. It's coming back now, or used to come back, to Springfields for conversion into powder and subsequent pellets. The pellets bit, as I mentioned earlier, I will leave to colleagues from Westinghouse and EDF to talk about. I'll skip through them very, very quickly. So how do we get from hexafluoride via powder to a pellet? And what we have to do is, I remember what we've always said, processes have to be reversible, or most of the processes have to be reversible. So we're going to convert this gaseous uranium hexafluoride into powder. And at Springfields, we were handling powder after the thermal denitration stage. If you remember, we actually handled naturally occurring UO2, but we needed to enrich the U235 content of that UO2 before we could use it on light water reactor, on AGR reactors. And how we convert it, very, very simply, and bear in mind, that's all we're talking about, very simple reactions. None of this organic chemistry where you have something like a 10-stage synthesis. That would be no good to us. It would be expensive. We did have, and I'll come back to did have in a few minutes, we convert that UF6 to UO2 simply by reacting with steam to hydrolyze the UF6 to UO2F2. Bear in mind, we have not changed the oxidation state. The uranium is still 6-valent. Oxygen is 2-, therefore we've got 2 of them. 4-. Fluorine is 1-, we've got 2 of them. So an extra 2 minuses, still got uranium 6+. It converted from UF6 to UO2F2 by reacting with steam in a kiln. Again, we prefer kilns these days to fluidized beds. The only fluidized bed we did operate at Springfields was in the uranium hexafluoride production. But here, yet another kiln, around about a couple hundred degrees centigrade. In the first stage of that kiln, we convert uranium hexafluoride to UO2F2, and we then react that UO2F2 with hydrogen. And what does the hydrogen do? It's a reducing agent. It reduces the uranium hex, valent state, U6 plus, down to U4 plus, i.e. UO2. Okay? Any of the fluoride gases coming out of that kiln are scrubbed with caustic soda to ensure that we are maintaining very good environmental conditions. Okay? So we've now got UO2 powder. Not quite the end of the story, because that powder is not quite in the same morphology, physical form that we would like. It wouldn't pelletize very easily and very readily. So we actually granulate it. We make granules of it. This is, I think, from a material scientist, becomes a very interesting part of the process. So we granulate the material, make the powder far more clumpy, far more bulky. Then what do? We actually comminute that powder, those granules, beg your pardon, down to powder. This is what we're showing here. Why? Because now that particular powder, if you like, has got the stickiness when we squash it together, when we pelletize it, to hold together. The original powder coming out of the kiln, out of the rotary vacuum kiln that we're showing on the rotary kiln, beg your pardon, we're showing there, that actually powder wouldn't do that. It wouldn't compress efficiently well. So we've now broken those granules down into powder, and we can now send that on for further treatment, either mixing with other materials, with other reagents that will help the powder to have a little bit more cohesiveness when we put it under pressure, or we may include one or two poisons, neutron poisons, such that we can control the neutron density and the heat in a reactor more efficiently. So we compress the powder into a pellet, and if you remember, or you may not, have you had the reactor module yet? No? Javad, do we know?
Yeah, well, have you done the N03, guys?
The reactor.
The reactor module?
Yeah,
we don't do reactors.
Yeah, we'll have it. Yeah.
Yeah, we have it.
You have. Okay. So you'll know about the big difference, therefore, between an AGR pellet and a light water reactor pellet. Yeah. John Turner. Not John Turner. The actual AGR pellet, if you remember, ladies and gentlemen, does have an annulus. It's a bit like a polo mint, but a little bit taller than a polo mint and a little bit less in diameter. But it has an annulus like a polo mint. The light water reactor fuel is smaller and does not have that annulus. The annulus there for the AGR pellets is for the fission product gases that are produced during the performance in a reactor. So this is what this particular part of this next slide is telling you, how we actually convert the O2 production, granulation and pelleting in actual pellets themselves. And I'm sure our colleagues from Westinghouse and EDF will be telling you more about that, excuse me, later, either tomorrow or whenever this week. And what I normally say to our colleagues on N04 or N02, particularly when, no disrespect to you, ladies and gentlemen, when we have a few more chemists on board, probably around about this point, granulation and pelletizing and subsequent fabrication of the fuel itself, the actual chemistry involvement starts to rapidly decline, and we get involved if there are problems with residues that require treatment or effluents that require treatment. But bear in mind, once we get beyond here, the pelletizing, and the O2 production, granulation, the pelletizing, producing the fuel assemblies, very little waste. because there's not many, if any, liquids involved. And liquid processes, aqueous processes, tend to generate far more effluents than, let's say, what we would call a pyrometallurgical process. Now, just very quickly, Javad, if I may, go back to here.
Okay.
That process, that's what's called IDR, the integrated dry route. Why is it integrated?
Sorry. Which slides are you? Because students are saying that they've fallen behind where they should be. What slides are you on right now?
That there. That's the integrated dry route.
So,
Why is it integrated? Because in one kiln, we do two processes. We hydrolyze the hex to UO2F2, and we convert the UO2F2 to UO2 by reduction with hydrogen. Integrated. Integrated dry route. Why is it dry? Because there are very few effluents coming out of this process. We don't use any liquids. The only liquids we use, if you remember, when I talked about the HF that's produced that comes off here, what do we do with that? We have to scrub that with, for example, alkali such as caustic soda, for example, because we're not allowed and shouldn't be and should not be allowed to discharge it directly into the atmosphere. So that's where the chemistry occurs with UO2 manufacture. And before Springfields, and it was BNFL Springfields that developed this process, before we did the actual conversion of the uranium hexafluoride into UO2 powder was a 7-stage wet process. And normally at each stage, you would produce a liquid waste. Reasons why BNFL, actually BNFL in 1970, probably around about 75, developed this process because they thought it was a game changer. To a large extent, it has been. I'll stop there because, as I mentioned, these particular overheads, and I'll just go back to now these particular ones, and this, for example, hopefully our colleagues will tell you all about from Westinghouse or from EDF.
yeah.
Javad, if they do not, then let me know. We'll try and
if they don't, I have other material to provide anyway. It's not and I've got series of videos as well that I can share if they did not cover. So I wouldn't worry too much about that.
If you don't mind, then I'll stop there.
Okay, so you've got some, basically, according to my screen here, you are on slide number 18. So you're not covering the remainder of the...
Slide number 18. Let me go back to slide number... What's slide number 18 then?
Yeah, so student, if you've said anything on the other pages...
Slide 18 is the IDR process.
Yes, okay. So have you covered your production, because they didn't see this?
I'll try and sort it out for Wednesday, Javad.
Okay, no worries.
I'll try and get the screwdriver and spanner out.
Is this the
Are
end
there
of...
any questions, ladies and gentlemen?
I'm going to stop the recording for the questions.